AB Calculus, Section 5.3, Definite Integrals. We're going to do a little review here to start for 5.1, 5.2, 5.7 by naming the following here first from those sections. An integral that you see here in the first case is called an indefinite integral. There are no limits of integration, right? So no number at the indices for that integral. Then you see limits from a to b on the integral of f of x, which we would call a definite integral. So anytime you see limits of integration, you will think definite integral. No limits is an indefinite integral. In 5.2, we talked about the integral of velocity, which gave us the total distance or area under the curve, right? And we used a couple different methods, right? We looked at a linear situation, right? Where if we traveled 75 miles an hour for 3 hours, the area under the curve represented the total distance traveled, right? And in this case, that ended up being 225 miles during that time frame. Then in section 5.2 and 5.7, we talked about approximating the area under a curve using 4 methods. We had our LRAM, left rectangular approximation, RRAM, right rectangular approximation, midpoint rectangular approximation, and then the trap method. I'm going to breeze through a few of these examples here. But we used each of those 4 methods to approximate the area under a non-linear curve. Okay, furthermore, we were approximating, as we just spoke, using each of those 4 methods. Now in this case, I'm going to do an RRAM on x cubed on 3 subintervals, it looks like. And let's just go out to 3, 2, and 1. So I'm going to do a quick RRAM. I'm going to find the right endpoint of each of those 3 intervals. I'm going to find those outputs, draw my rectangles, and the area under that curve, of course, will be an approximation for the integral from 0 to 3 of x squared dx. Okay, so approximately equal to, of course, we would have areas of 1 minus 0 times 1 squared plus 2 minus 1 times 2 squared plus 3 minus 2 times 3 squared. So the area under that curve comes out to be approximately equal to 1 times 1 plus 1 times 4 plus 1 times 9, which was 14. And we looked at that in a previous example on a prior lesson. Okay, so suppose f of x, or the height, is negative. And we've talked about this, right? We talked about how as we accumulate negative areas, or if the function is negative, we accumulate those areas in a negative sense. Okay, and then we just sum up all of our areas. The Riemann sum gives the negative of the area because the area is always positive. So we'll look at an example on the next slide and see what we mean. Okay, so we've also looked at this example in a previous lesson. I believe it was the last lesson. We identified these 4 points. So the point 30 will be there, 0.23 would be here approximately, 4, -2 would be right about here, and x equals 5, -5 would be there. Okay, so if I did an RRAM also here, take the rightmost point, and I draw my rectangle. Now the second rectangle that I'll see clearly will have an area of 0. And each of the other rectangles will have their own specific areas based on their width and their height, of course. So we're going to go from 0 to 5 of f of x dx. Of course, our first rectangle here would have a width or a base length of 2 minus 0 and a height of 3. Our second rectangle, of course, has a width of 3 minus 2, but has a height of 0, right? You can see the height here is 0, so clearly that will not accumulate any area. Our third rectangle, right here, is going to have a negative area. So we're going to take 4 minus 3. That'll be the base length of the rectangle. The height will be negative 2. So this is going to, of course, accumulate a negative space for us. So will the last rectangle. We'll take 5 minus 4 times f of 5, which of course is negative 5. So yet again, we'll get a negative area. Here we'll get a negative 2. And in our last rectangle, we'll get a, oops, didn't need that, negative 5. Okay, so our first rectangle accumulated an area of 6, second 0, third negative 2, and fourth negative 5. So when f of x is greater than 0, the area is positive. When f of x is less than 0, the area is negative. Okay, let's look at another example down here. A big summary that we talked about in our last lesson was the difference between displacement and total distance. So displacement is the same as a net area, and total area is the same as total distance. Okay, so if we were to take these three spaces, right, we were to integrate from, let's say, x equals 0, we'll call this x equals a, x equals b, and x equals c. If we were to find the integral from 0 to c of, and we're going to call this this function v of t. If I just wanted the integral from 0 to 3 of v of t, that's going to be considered the displacement, right? This would be an example of net area or displacement. So to find my three areas, of course, I'm not going to approximate. I'm just going to look at the numbers given. Of course, the 10 is above, so that would be a positive 10. The 30 is below, that would be a negative 30, and the 50 is above. So our net area would be 60 minus 30, which is 30. So the displacement is 30 units, whatever that might be, meters, feet, whatever. The total area is an example of the integral from 0 to c of the absolute value of v of t. Okay, so we would have the absolute value of 10, which is of course 10. We'd have the absolute value of negative 30 and the absolute value of 50. When we talked about Johanna in the previous lesson, that was a good example of that. Okay, so we're going to take 60 plus 30, that'll be 90. So the total area, or the total distance traveled, of course, would be 90. All right, let's continue. Okay, so the idea of finding the exact area under a curve becomes relatively abstract. So I'm going to read this, and then we're going to go ahead and draw something out. So the Riemann sum to a definite integral. Our goal is for you to understand the meaning of an integral and be able to write an integral as a Riemann sum, as well as the other way around, a Riemann sum as an integral. The definition of the definite integral as a Riemann sum is if f is a continuous function defined for this closed interval from a to b, we divide the interval a to b into n subintervals of equal length, where delta x is b minus a over n. I'll explain in a moment on that. We choose sample points in the interval so that the ith sample point lies in the ith interval. Okay, so let's make sense of that. All right, so let me draw myself an axis. Okay, where this is f of x, this is x. Let's go from x equals 0. Okay, and let's let's identify these values, x equals a and x equals b. All right, let's draw ourselves a function. Go red. All right, here's our function f of x. Okay, now let's talk about an RAM in this situation. But what we're going to do is we're going to take this interval from a to b and we're going to split it up into n subintervals. So how we're going to do that is we're going to take b minus a and divide it by the number of subintervals we want. Okay, so if I split that up, this would be the first, second, third, imagine, and then this would be the n minus second, n minus first, and then x equals b will actually be our nth, the end of our nth subinterval. Okay, so let's talk about these subintervals. Of course, this would be x equals a plus 1 delta x. Okay, we're going to call the width of each subinterval delta x. Okay, our second interval, or our second x value, we're going to call x equals a plus 2 delta x. This third one will be x equals a plus 3 delta x. Okay, and then I'm going to go to the second to last and the last. So this would be x equals a plus n minus 1 delta x. And then x equals b is actually equivalent to x equals a plus n delta x. Right? It's the nth, end of the nth interval. Okay, so let's draw these out. Okay, I'm going to draw some rectangles. And we're going to do a right Riemann sum. So we're going to go all the way out to b. And there is the nth subinterval. Okay, and then I'm going to go out to the n minus 1th subinterval. You can see that take shape here. And so on. Okay, so I'll go all the way back here to the third subinterval. The second subinterval. And the last would be the first subinterval. Okay, so now what we're going to do is we're going to generalize. Right? We're going to generalize the integral from a to b of f of x. So right now, we could say that that's approximately equal to. Okay, let's take our first rectangle here. Okay, so we're going to take f of x, which would be f of a plus delta x times delta x. Okay, so what do I mean by that? Okay, this delta x is the base length, which is the width of this interval. F of a plus delta x is this height. Right, it's the function output at this x value, a plus delta x. Okay, let's do our second. Okay, so our second rectangular area will be f of a plus 2 delta x times delta x. Okay, identify what's going on. Here's the base length, delta x in width. Height is the output when I plug in a plus 2 delta x. Okay, now I'm going to skip the third, and I'm going to go all the way to the nth. Okay, so I'm going to go to the nth rectangular area. And actually, I'm going to put it in yellow, just so I can keep these straight, so the blues don't show up twice. Okay, so I'd go the third, fourth, fifth rectangle, all the way up to the nth rectangular area, which would be this. f of a plus n delta x, which you could call f of b times delta x. All right. Now, one thing we could do is we could take out a delta x. Since they're all the same, take that out. And what we've got is this summation, a plus delta x, f of a plus 2 delta x, all the way out to the nth delta x. So it'll be f of a plus n delta x. All right, this summation right here is the same as the following summation notation. I'm going to take the sum from I equals 1 to n of f of a plus I delta x. So let me explain what that means. Okay, so if I plugged 1 in for I would get f of a plus 1 delta x. That's our first term in this series of terms. So this means sum to add. Then we would iterate with the second term. So we'd plug in a 2. That would be f of a plus 2 delta x, all the way up to the termination of our iterations, which would be the nth term. This represents right here this summation, including all terms that we've kind of collapsed here, so to speak. All right, then I'm going to multiply by, of course, delta x, this value right here. Okay, so this summation is an approximation of the integral from a to b of f of x dx. Now, how is it that we could make this more and more and more accurate to the point where we could actually say that they are equal? Well, what we can do is, of course, we're not going to change anything with our notation on the left side. What we're going to do is we're going to take the limit of the summation as n approaches infinity. What that does is that squeezes and compresses, so to speak, the width of each of the subintervals to the point where those widths are headed towards 0. All right, so if the finite interval of a to b now has, let's say, 100 subintervals, right? Then these little errors right here are going to be very, very, very small. And the larger the number of intervals, the smaller the width of the interval, the smaller the error. So this right here, let me bubble this in. This is the formal definition in sigma notation, right? This is the Riemann sum for a definite integral. So we're going to be able to take a definite integral, turn it into a Riemann sum, as well as the other way around. All right, let's take a quick look at what we've got here down below. This notation here is slightly different than what we have below, but this x sub I just represents, here's our first x value, second x value, third x value, fourth x value, etc. Okay, now we're going to work primarily with this form, but this is another equivalent form down here. Okay, so a Riemann sum is the sum of the areas of the rectangles that lie above the x-axis and the negatives of the areas of the rectangles that lie below. An integral, this symbol, is a signed area. All right, let's get into a few examples of how to transfer from one form to another. Okay, example 3. Which of the following limits is equal to the integral from 2 to 5 of x squared? Okay, so my recommendation to you is to, in each of these examples, try to identify these values. Okay, so the integral goes from a to b. So a has to be 2, b has to be 5. So delta x, of course, is going to be b minus a over n, which will be 5 minus 2, which is 3 over n. So what would f of a plus I delta x be? Well, first of all, you got to know what f of x is. F of x is the function that we're integrating, x squared. Therefore, f of a plus I delta x will be f of a, which is 2, plus I delta x, which will be 3I over n. Now, in some cases, they might not refer to this index as I. It might be a k or something else. I think in this case, they utilize k. So now what we want to do is we want to rewrite this in the limit notation that represents the Riemann sum for that definite integral. So this will be the limit as n approaches infinity, summation from k equals 1 to n of f of a plus I delta x, which will be 2 plus 3k over n squared times delta x, which is, of course, 3 over n. And it looks like in this case our answer would be D. Okay, example 4, let's go the other direction. We're given a definite integral. We want to write it as a Riemann sum. Okay, yet again, we want to know A, we want to know B, we want to know delta x, and we want to know f of A plus I delta x. I like I, you don't have to use I, you can use k if you'd like. So A is 1, B is 3, so delta x is 2 over n. So f, of course, is 1 over 2x minus 7. Therefore, f of a plus I delta x will be 1 over 2a, which is 1, plus 2I over n minus 7. Okay, so look at this now. This is the shell of f of x with a plus I delta x inserted into its independent variable. Okay, so this will equal, this definite integral will equal limit as n approaches infinity of the summation from I equals 1 to n of f of a plus I delta x times delta x. All right, there you have it. That would be an equivalent statement in Riemann sum form. Let's continue with another example. Okay, let's look at example 5 and 6 on this page. Okay, you can see that we've got a Riemann sum here. And we've got the limit as n goes to infinity of 1 over n, which is going to be delta x. So if delta x is 1 over n, then that tells me that b minus a is equal to 1. Okay, so that's good to know. This summation right here, you can actually see, here's our a value, and here's our I delta x. Right, we know delta x is 1 over n, so you can see you got 1 over n, 2 over n, all the way up to n over n. Therefore, if I rewrote this as 1 over n times the summation from I equals 1 to n of 1 over 1 plus I delta x. We can clearly see, well, first of all, we know that b minus a is 1. I can see a showing up here. A is equal to 1, therefore b would equal 2. Now when it comes to f of x, I know that f of a plus I delta x is going to be 1 over a plus I delta x. Therefore, f of x is going to equal 1 over x. Okay, so what we can do now is we can build our definite integral. This will be equal to, of course, the integral from 1 to 2 of 1 over x dx, which of course in this case will be e. Okay, let's look at another example, example 6. If n is a positive integer, then the limit as n approaches infinity of 1 over n times that summation can be expressed as the following integral. Okay, very similar. We see delta x is 1 over n, which tells us that b minus a is equal to 1. Okay, now let's look at our summation. I'm going to rewrite our summation slightly so that we can see what's happening here. All right, I got delta x. Now I'm going to expand each of these slightly. Okay, and you'll see exactly why I'm doing that in just a moment. I can see the iteration happening, and I'm going out obviously to the, in this case, n minus 1th term, but doesn't really matter. Okay, it doesn't matter if you go out to the n minus 1th or the nth. This is actually likely a left Riemann or left rectangular approximation method using that. But you can see that a here is 0, right? It's 0 in all cases. So I can see that this is my first delta x, second delta x, all the way up to my n minus 1th delta x. So what is my value for a and b? Well, I know a is 0, and I know from above b minus a is 1, so that means b is equal to 1. Now f of x is where it gets interesting. I know that f of a plus I delta x is going to be 0 plus I delta x, or I times 1 over n, right? So f of x in this case will be, oops, I'm sorry, that should be squared, will be, of course, x squared. So I'm going to find the integral from 0 to 1 of x squared by using that Riemann sum. And it looks like our answer to me ends up being A. Very good. Let's continue. Okay, now we're getting to example 7 and example 8. And you'll notice that we've dropped the limit notation as n approaches infinity. Therefore, whatever this summation is equal to is going to be approximately, not exactly equal to, but approximately equal to some integral. Okay, so I don't know what it is yet. Okay, I got to fill in the blanks, so to speak, here. But I can see delta x. Delta x is equal to 1 over 20. So there's 20 rectangles here. So that right there tells you, since I'm not seeing 1 over n show up, that this is an approximation. Okay, I see b minus a is equal to 1. Now as I look at this, right, I can see that I got the summation from I equals 1 to, it looks like 20 of the square root of, let's say, 0 plus I times 1 over 20. Okay, so it's interesting here, and of course I'm multiplying this whole thing by 1 over 20, which is just delta x. But you can see that a in this case is 0. I know b minus a is 1, so b is equal to 1. And f of a plus I delta x would be equal to the square root of 0 plus I delta x. Therefore, f of x is equal to the square root of x. So this is equivalent to the integral from, or approximately equal to, the integral from 0 to 1 of the square root of x. Kind of cool. All right, let's look at example 8. Okay, I see delta x. Again, this is going to be an approximation. So delta x, of course, which is b minus a, all right, which is 1/30th. So there's 30 rectangles approximating this. Okay, so b minus a is equal to 1. Okay, now, again, my summation It's going to be from I equals 1 up to 30 of the sine of 0 plus I times 1 over 30. Okay, and of course we bring along delta x. Okay, so a is equal to 0. See that right there. B would have to then be equal to 1. F of a plus I delta x is going to be equal to sine of a plus I delta x. Okay, so f of x is equal to the sine of x. There it is. Okay, so our integral expression is going to be from a to b, so 0 to 1 of f of x dx. 0 to 1 of sine of x. Boom, there it is. B. All right, let's continue with a few more examples. Okay, example 24, very, very similar example number 9, very similar to example 7. This is actually going to be the integral from 0 to 1. Okay, now kind of interesting the square root of x. Okay, so it's the exact same answer, actually. So there you go. But as you look at this, look at kind of where we're starting. We're starting close to 0. We're ending up very close to 1. Okay, of course, this is delta x. Right, and then we got, our summation on the inside. Okay, let's continue with example 10. If you do want more help with example 9, you can kind of look back at example 7 or come ask your teacher. All right, which of the following limits is equal to that? Okay, so this is the easier of the two to transition from indefinite integral to a Riemann sum, at least from my perspective. But a is 3, b is 5, delta x will be 2 over n, f of a plus I delta x. We'll get that in a second. What is f of x? F of x is x to the 4th. Okay, so I'm going to take a plus I delta x, so that'll be 2I over n, and I'm going to multiply it take it to the 4th power. Okay, so we know that the integral from a to b of f of x dx is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of a plus I delta x times delta x. So we just have to kind of fill in the blanks, so to speak. So this will be the limit as n approaches infinity. We're going from 3 to 5 of x to the 4th dx. So we're going to take the summation. Looks like they use k again. I can work with k. F of a, 3 plus 2k over n to the 4th times, of course, delta x, which is 2 over n. Let's see if we can find that, and it looks like D. Boom. Points in the bank. Let's keep going. All right, the next few examples here are definite integrals, but we're actually going to look at them geometrically, which just means we're going to look at the graph. Okay, we're going to then determine the area based on the graph. So we don't know how to integrate some of these functions yet, right? But geometrically or graphically, we can look at them, find shapes, and then their areas, typically triangles, trapezoids, rectangles, or circles, potentially. So example 11, this is the integral from -4 to -1 of pi over 2. Now pi over 2 is just a constant, it's a value. It's just above 1.5. Yeah, just above 1.5. So I'm going to sketch a graph, okay, where my function, right, is y equals, theta. Sorry, my independent variable is theta equals pi over 2. Okay. Actually, I think I got that twisted a little bit. Let's call this y. Right, because theta is the independent variable right here. Okay, so y equals pi over 2, and we're going to integrate. That's just a horizontal line from -4 to -1. Well, that's pretty simple. It's just going to be a rectangular space. So the integral from -4 to -1 of pi over 2 d theta will equal, geometrically, just the base length, which is 3, times the height, which is pi over 2. So this area should be 3 pi over 2. And we can be confident that that's exact due to the linear nature of the function itself. Okay, example 12. Use the graph of the integrand and the areas to evaluate the following integral. Okay, so the integrand, let's get into that for just a moment. The integrand is this function, square root 16 minus x squared. Okay, so what the heck does that look like? All right, so if y equals the square root of 16 minus x squared, I'm going to do a little work here. I'm going to square both sides, and something will kind of show up to you. I'm going to add x squared to both sides, and then I'm going to rewrite this in this form. Okay, this equation right here is the equation of a circle with a radius 4. Okay, now it's asking me to integrate just positive square root of 16 minus x squared. So let's graph this thing. So we're going to have a radius of 4, so this point will be -4, 0, and +4, 0. So a little mini lesson here. The square root of 16 minus x squared is above the x-axis, and negative square root of 16 minus x squared would be below. Now all we're asked for is the integral from -4 to 0 of the upper portion. So we're going to find this area right here in quadrant 2. Okay, so that area, -4 to 0, square root 16 minus x squared. I'm not going to actually try to do any, calculus here. I'm just going to take 1/4 the area of a circle with a radius of 4. I gotta square that. So that's going to be equal 1/4 times 16 pi. So that area, right, in blue there would be 4 pi units squared. I don't know what units are here in this case. Okay, 13. Longer set of notes here, guys. Apologize for that. Actually, I don't at all, because this is good stuff. But I'm going to graph the absolute value of x plus 2 from -2 to -1. So imagine the absolute value of x plus 2. That's a function, absolute value function, that's been shifted left 2 units. Okay, so the absolute value function, with no stretch involved, to the right of its vertex will have a slope of 1. Okay, and then to the left of its vertex will have a slope of -1. Okay, now we just want the area from -2 to -1. So we're going to find the area here from -2 to -1. All right, so that means we're going to find the area of a triangle. All right, so we got to find the base and the height of that triangle. So the integral from -2 to -1, absolute value of x plus 2 with respect to x will be 1/2 base times height. Well, the base is 1 and the height is 1. All right, so here's the base. Boom, here's the height. Okay, and that's a right triangle, isosceles right triangle to be exact. So our area will be 1/2 square units. So guys, the point of this page is that you may not know, and eventually you might not even know, the definite integral or the antiderivative of an absolute value of, a portion of a circle, or our first example, which was just a horizontal line. It might fool you, but if you sketch it, the graph geometrically can be helpful. All right, we got a couple slides left. Let's get to it. Okay, on this slide here, there's some information about integrable functions, okay, and properties of definite integrals. So I would advise you to pause the video and read through this. I'm not going to spend the time to read it for you. You're big kids, you can do it yourself. Okay, but spend some time, pause the video, take a look at this information, and know that you can and will utilize this information eventually. So I'm going to continue to the next slide. Okay, integrals of even and odd functions. So there's some interesting information here with even and odd functions. If you consider, let's say, an odd function. An odd function, for example, would be the function f of x equals sine x. Okay, what this information is telling us is that if you integrate symmetrically about the origin, right, so for example, from negative a to a of some odd function, then that area will be 0. That's interesting to look at. So I'm going to graph sine x. And I'm going to graph sine x from, let's go, right, this x value here would be negative pi over 2 out here to, negative pi out to pi. All right, so you can see this area here would be negative. This area here would be positive. They would be equivalent, right? And therefore, the area from negative pi to pi of sine of x would equal 0, right? It's an odd function. I have integrated symmetrically about the origin, and therefore that area would equal 0. Similarly, if I took an even function, let's take the function cosine x, which is even. Okay, so let's go g of x is equal to cosine x. And if I were to integrate that from negative pi to pi, let me see if I can sketch this accurately. It would look like this. All right, you can see from negative pi to pi. Okay, that's probably a bad example, right? Because those will negate each other. I'll go actually out further. Let's go out here to negative 3 pi over 2 to 3 pi over 2. Yeah, let's do that. Okay. What you can see is that this area here, if I were to sum this up, and this area here, they're going to be the same, right? The area to the left of the y-axis, the area to the right of the y-axis, they're the same. And therefore, the integral from negative 3 pi over 2 to 3 pi over 2 of cosine of x is going to be equal to 2 times the integral from 0 to 3 pi over 2 of cosine of x. Now, I don't know what that is. I don't really care. I just wanted to show that property. Okay, integrals of constant functions. If f of x is equal to c, where c is a constant on this interval, then the interval, or the integral from a to b of f of x will just be equal to c times b minus a. So check this out visually. Let's say f of x equals c. We had the pi over 2 example earlier. Okay, and we're integrating from a to b. So if we have a constant function, just a horizontal line, then what we end up getting is that the integral from a to b of c dx just ends up being a rectangle where we take the height times the base. Okay, so if you have a constant, just take the interval, right, b minus a, multiply it by that constant. Okay, integrals on a calculator. This is really helpful. Your calculator can do a ton of stuff for you. There's 2 ways to compute, graphically and numerically. Okay, typically what I use is the numerical method. Okay, and if you take your calculator and instead of pressing Math 8, you press Math 9, you're going to get something that looks like this. Right? It's kind of like your Math 8 notation that showed up. Right, and all you're going to do is you're going to plug, a, b, f of x, and x. So for the first example, you'd plug in a -1, a 2, x sine x, and then an x here. Press enter, boom, done. Okay, same thing for part B, 0 to 1, plug them in here, 0 to 1. Put this function in here and an x in there. Enter, done. Same thing for C. The key, the one thing you need to remember is make sure that you are in radian mode. Okay, make sure of it. All right, let's look at the last couple slides. Okay, example 15, wow, we're on example 15, is going to utilize some known information. We don't know much about what these functions are, but we do have enough information to still compute the following integrals. Okay, so I'm going to use something called the constant multiplier rule here. And I'm going to say that the integral from 1 to 4 of 4 times f of x is equivalent to 4 times the integral from 1 to 4 of f of x. Now, if I know what the integral from 1 to 4 of f of x is, which I do, it's 7, this would simply be equal to 4 times 7, which is 28. Okay, so using some information without actually knowing what the function is or looking at it geometrically, we don't even need to. For part B, I would just take and work these integrals separately using the difference rule. So I take the integral from 1 to 4 of g of x, subtract the integral from 1 to 4 of f of x. Well, I know g of x from 1 to 4, that's 2. I know f of x from 1 to 4, that's 7. So we would get 2 minus 7, which would be an area of -5. Okay, very similarly, I would use both of those rules that we just looked at. 8 times the integral from 1 to 4 of f of x minus 7 times the integral from 1 to 4 of g of x. So the limits of integration and the integral itself distributes over the functions that are given. That would be 8 times 7 minus 7 times 2. I believe, hold on, f of x from 1 to 4 is 7, that's good. G of x from 1 to 4 is 2, that's good. Therefore, I would have 56 minus 14, which is 42. Okay, part D. The integral from 1 to 4 of negative f of x, that's going to be equivalent to the integral from 1 to 4 of f of x times -1, which will be -7. Okay, now if we were to have situation E here, this is kind of interesting. The limits are flipped, so we go from 4 to 1. Now, one of the rules on that slide that I told you should read through, one of the rules is if I flip the limits, I change the sign of the area. And therefore, yet again, I'm going to get the same answer as I did in part D, which will be -7. All right, one more slide to go here, guys, and then we'll be done for this lesson. Okay, I'd encourage you to pause the video and attempt to find each of these areas, and then come back and watch me finish this thing up. Okay, part A, I'm going to take the integral from 0 to 2 of f of x. Now, if it were me, I would just look at this geometrically clearly, and from 0 to 2, I see a rectangle and a quarter circle. All right, so I see a rectangle. Let me kind of show you what I'm talking about. See a rectangle that's base of 2, height of 3. So that would be 6 plus this quarter circle right here, which is 1/4 of a circle with a radius of 1. So that's going to be pi over 4. Okay, 1 to 3. Now I'm going to split this up. 1 to 3 would be a rectangle with a base of 1, height of 3. So that'd be 3 plus that quarter circle. Oops, I'm sorry. Actually, I'm going to have 2 rectangles and a half circle. So I would have 3 plus pi over 4, and I'm actually going to double that. So that would give me 6 plus pi over 2. Very nice. Now for part C, I'm going to go from 0 to 5. And I'm actually going to do that in an interesting way. I'm going to do 2 spaces, 0 to 5. I'm going to find the area of this trapezoid. You can do it a different way. It's totally up to you. I'm going to find the area of that trapezoid, which will be a half. Base 1, base 2 will be 5 and 3. And the height will be 3 as well. So this height 3 is this height here. Okay, and then I'm going to add to it a half circle with a radius of 1, so that'll be plus pi over 2. Therefore, the integral from 0 to 5 of f of x will be 12 plus pi over 2. All right, now the integral from 1 to 5 is going to be the same as the integral from 0 to 5, but I'm going to take away 3. All right, I'm just going to take away that rectangle right there, which will leave me with 9 plus pi over 2. Hey, a long set of notes, but some good information there. So I hope you take it in. Let me know if you got any questions. We'll see you in the next video.